Before we manifest a multi-agent AI syndicate on this hardware right here, which is a Chewy with only 16 gigabytes of RAM, not VRAM, only 500 gigabytes of storage, we're going to have to master the hardware. You don't really need a $5,000 rig to be operational. What we need to do is take control of our resources. Most people let Windows start to dictate their performance, but in our case, we're going to dictate the hardware. We're going to start on this scaled down hardware, this Chewy, because if we can win here, if we can get everything tight on this machine, then we can win anywhere. So now we're going to clean up the Windows side of this and reclaim about 5 gigabytes of high-speed runway. And we're going to do it in just a couple of minutes. So as you can see here, currently floating around 60% of my RAM being used. And that's with my coding music on in the background. That's with my Google Chrome windows open. And we want to scale that back. I want to compress a lot of that because I don't want all that stuff slowing me down when I start coding with my offline AI on my hardware. I created this shell script right here, and I'm going to go through it line by line so that you can see exactly what I'm doing to take back my hardware, the tasks that I'm killing and getting rid of, the memory compression that I'm about to perform, and exactly what all that's going to look like. And then we'll see what the results are from the 60% of my RAM that's being taken up now to what will be taken up afterwards. So task kill, this is our primary mercenary. It's our standard utility. How we're going to use it matters. We're going to use it with this /f, which is our authority flag. It's going to tell the operating system that we're not asking for permission here, but we're terminating the process immediately. This /im is the image name. So we're going to hunt down by name, not just some volatile process ID. We're actually targeting specific manufacturer bloatware, which has absolutely no business running during a high-level build, which is all the AI stuff that I'll be building. So we're targeting things like this Chewy updater service. And then we don't need Microsoft Photos running in the background when I'm not even using it. This /t right here is saying, hey, we don't want any survivors when we cut off these processes. We want to eradicate the tree. We want to wipe out the main process. And we also want to get rid of all the child processes that it spawned in the shadows. Phase 2 is our compression engine. We want to enable this MMAgent. So that is a memory manager agent. It's really the hidden governor of my RAM. And most users will just leave this on auto, but we want to take manual control because of the level of projects that I want to perform on this level of hardware. The MC right here, this MC right here is our memory compression. This is our Windows version of ZSwap. Instead of dumping our inactive apps to the slow SSD, this tells the CPU that I want you to zip them up into high density chunks of my RAM. And then we're mathematically expanding our 16 gigabyte runway so that we can actually be way more efficient with this machine. The next thing we want to do is we want to restart our service. So restart service is a command that's going to stop our background processes. And then we are hitting sysmain, the engine that handles compression, to force it to reevaluate our 100+ processes that we have running in the background that we really don't need. And that's just bloating up my entire system. Memory here, this money sign is the variable, or it's what declares a variable. So we're creating a digital container to hold a connection to the heart of the operating system. This get WMI object, we are reaching into Windows management instrumentation. This is a deep level interface used by enterprise admins to manage entire server farms. We're using it to manage this one machine. Our empty working set right here, this is the global flush. It sends a system-wide signal to the kernel to audit every background app and return its unused weight to the pool of memory. This DLL import right here, this is the hook. We are reaching outside of PowerShell and directly into a core Windows system library, which is called psapi.dll. We are grabbing a surgical tool, usually reserved for the operating system's kernel itself. With this add type right here, we are taking that raw C and compiling it into a functional tool inside of our session on the fly. This pass through right here, this ensures that the tool stays hot and active so we can trigger it for every process. Our actions silently continue. This is clean engineering. It ensures that if we run the script twice, it doesn't clutter the terminal with errors about the tool already existing. With get process here, we fetch a list of every single active process and then we pipe it. That vertical bar, that's the most powerful character in terminal history because it moves the data from one command to the next. And then for each object right here, this is going to be our loop. For every app found, we execute the action inside these curly brackets. This money underscore right here is actually a placeholder for the current app. The .handle is the unique digital ID Windows uses to talk to that app's memory space. The try here and the catch here is high-level error handling. If a system process is protected, we don't crash, we simply skip it and move to the next target with total efficiency. Now we are going to just run our shell script. So we got a method not found error on our WMI. So we'll just fix this and then we'll actually run it. What happened there is Windows is actually transitioning from an old language and it's moving from that WMI to a modern, faster language called CIM. On a high performance hardware, the old WMI hooks are being tossed on out. So we're going to pivot to the CIM instance. It's cleaner, it's more secure, it's now the professional standard for 2026. So we went from Windows Management Instrumentation, which was technology from the 90s, into Common Information Model, CIM, and it's the cross-platform industry standard now. So it uses WSMAN, web services for management. It's lighter on the CPU. It's designed to work across different versions of Windows without breaking. Win32 operating system, it's just a specific class or chapter of the Windows brain that we're talking to. By calling on this, we're telling the PowerShell, I don't want to talk to a single app. I want to talk to the operating system itself. With our empty working set, this is actually the method. Once we have the operating system in our hand, thanks to the parentheses, we trigger the empty working set here. And what it does is it tells the kernel to reclaim every single page of physical RAM that isn't actively being used by a process's core logic. Essentially, Windows is just not going to let me do enterprise level stuff at my personal computer. We're having to switch up the methods in order to get the results that I want. As you can see here, I dropped from 60 something percent memory with my YouTube music and my Google Chrome's open and all that stuff and my OBS running. But at the same time, I want it to be less than 50% because I want it to be absolutely as optimal as can be. Even though Windows won't let me do what I want to do, we're going to get rid of the cache and we're going to do a couple other things to drop these numbers down. Remember, I'm still playing my YouTube in the background. I'm still got all these tabs open so that I can see exactly what the actual effect will be when I'm in a workflow. So we've got our DLL import, Kernel32.dll. We are reaching past the user interface and directly into Kernel32. This is the primary library for the Windows kernel. If WMI or CIM are the front doors that Microsoft locked on us, then this is the foundation of the house itself. This set system file cache size right here, this is a privileged command used to tell the Windows file manager to dump its standby data. It's normally used by high-end server database engines. We're using it to clear out our personal runway right now. All right, we run this again, and all these true statements right here, these things that say not found is because I already killed them before. All these true statements are everything that we wrote down actually working and clearing things out, and then there's our success message. And just like that, you can see how we actually reclaimed quite a bit of our memory. It was at 40% just a moment ago, but we went from 61% to between 40 and 45 about. I'm recording with OBS. I'm listening to YouTube music. I have multiple browsers open. I have multiple terminal shells open. So to take that down from 60% to closer to 40% is definitely a sweet spot. And as you can see, I got it in the 30s after running my ready1.ps1 script again. So we took essentially from 60 down to 37. Now stuff will pop back up. Things will fight for the memory, but when I'm recording, when I'm sitting here listening to music, having all these different apps open, having these background process running, to have it closer to in the 30s is much more optimal. So if you're running offline AI, if you're trying to keep your cloud costs down, then you're probably going to want to use a shell script like what I have. I will include that for you, that if you want to try it, do so at your own risk, mess with your hardware at your own risk. But here it is. This is going to make sure that my 8 gigabytes of RAM that I've given to Linux to run my AI Syndicate with my Qwen 2.5 coder brain, quantized model, obviously, that's going to take up a lot of weight. So I'm going to use ZSwap and hopefully compress all that other stuff down so that my brain can run at a high level. I can use my Jelly code to build out my entire Ocean Jelly AI Syndicate and build all my apps with that. Completely offline, completely sovereign, completely autonomous. I'll leave that script for you down below if you're using Windows and you're using PowerShell. It might be of use to you. And as you can see, we've leaked a little bit back up to 40. But if I was going to go record OBS right now, then I just run that script and it's done. And we kill a lot of that RAM and we make things run much more smooth. All right, I'll see you in the next video.